All right. Thanks, Ankrish. Thanks for having me. This venue has grown. Nicely done. This is always a pleasure to be here. I can't see my slides. Yeah. Okay. So I'm Daniel. I'm a professor at Georgia Tech. I work on side channel analysis, mostly microarchitecture stuff these days. And the title for today is Side Channel Attacks, Lessons Learned or Troubles Ahead. And again, thank you for having me here. So as I was laying out this talk, I was start thinking about, okay, so what are these side channels? What is going on? And how did we end up in this mess that we are there today? So at least from my perspective, and here's a disclaimer, by no means this timeline is accurate or historically correct, but it serves my narrative, so let's go with that. Okay, so this started from this microarchitectural mess that we are in here today. Started around 2005, when this was mostly a deal about cryptographers and crypto nerds freaking out about math. We have here Alice, we have Bob, we have their key. They're trying to figure out the key between Alice and Bob, and then there is this story about Eve trying to extract the key from Alice and Bob. Okay, and math nerds, and I had full disclaimer, I'm one of them. Oh, we love this problem. Like, you can freak out about AES for as much as you want, and we spent roughly a decade freaking out about AES. And then this happened, where it's, forget about the crypto, forget about AES, forget about RSA, has nothing to do with it. This is all your data, all your time, your entire system is compromised, and oh my god, what is going on? Fast forward a few years, this kind of got aggravated by having many logos. Each of these attacks comes with this cute emoji, and like it's everywhere, it's all the time. I can't deal with it. Nobody knows already what sets one logo apart from the other logo. We're just being overflowed with logos, and that's it. Okay, so here's how we ended up in this mess, at least from the attacker's perspective. Computation also evolved, and there is a parallel timeline here, which is again not historically accurate, but narrative serving. Okay, so in the 90s, heavyweight computation was mostly about Intel and x86, and computers looked like these bulky items that sit on our desks, and humans usually move between computers. So computers don't move, they sit stationary, and they ingrown themselves in with wires, and then humans jump around between computers. Moving on another decade, well, now we see the rise of mobile computing, and devices are no longer ingrained on desks, we move them around. Okay, so it's more about people-facing and not device-facing. It's more about the human experience of the device's user, so it's personalized for one user having many devices. And then this got even stronger these days, where like if you look at me right now, not counting my laptop, I can probably count 5 computers on my body already. And it's less and less about x86 and Intel, and we see the rise of alternative platforms, more that are more power efficient, more energy efficient, have more computing resources, and we're moving away from x86 with the rise of ARM, Apple, and others. Okay, great, right? This is how this changed. So let me clean up the slide a bit. Okay, so these two logos have been a utter disaster. It's been 6 years. Okay, so hardware is hard. Hardware.io is harder and therefore fun. Okay, hardware has slower life cycles, and we keep on saying that hardware takes time to do. Great. It's been 6 years. Okay, the devices that we have right now are the second generation of post-meltdown devices. No excuses. It's been 6 years, right? We had time. So, the questions for this talk is, are we doing better? Did we actually learn our lesson? And can we actually use all this knowledge for something productive? Okay, and this is the academic clean version of these questions. The less clean version, if you like to think in pictures, here's a picture of me. I did a lot of mess, and what ideally you would like to do is something like this so I can go home. Okay? Here's another way to think about it. So what is all this Spectre and Meltdown mess that happened to us in 2018? So here's a piece of code, and it's basically an if statement. And if you have an if statement, you have a branch predictor. And hey, look, this code is actually kind of safe, right? Because I'm checking that x is less than array len. So this code will absolutely not have an integer overflow. It absolutely will have an integer underflow because I forgot to check that x is positive. But you know, university professors, we don't code that well. So let's ignore that problem right now. Okay? So in principle, I'm allowed to execute this function on any small value of x and everything will be just fine. Right? You put smaller value of x here, x is smaller than array len, you bring array len to the cache to decide that, and then you execute array of x, get back a value I, multiply I by 256, get back a value y. Okay. And all of you that expected something wrong to happen here, well, absolutely nothing wrong happened here. I just wasted 30 seconds of your life. You're welcome. Okay? But hey, you followed that code, which was the point of this. Okay. Now, every time we have an if statement, when it comes to a modern CPU, we also have a branch predictor. So this branch predictor, go execute this code 1,000,000 times. Eventually, we'll learn that this branch is usually taken. And here's when the nasty surprise comes in, of course, because if I plop a large value of x in here, whee, boom. Okay, so now what? Well, okay, is x smaller than array len? Well, the short answer is I don't know yet from a CPU perspective because I don't have array len. I need to bring array len into the cache to figure this out. I don't know quite yet what's going on, so I'm going to fall back to branch predictor because CPUs wait for no one. Okay? And because past behavior shows that this branch is usually taken, let's go right in it. Of course, now you have a pretty serious buffer overflow, and you leak the result through a cache side channel, which you then analyze the latency of the cache and figure out what's going on. Now, yes, this code will result in an error, and you will get your error message, but too little too late, because by then the data has already leaked through your cache footprint. Why? Because the cache footprint right here is basically the value times the value of secret times 256. So that's Spectre. Okay, here's your 3-line preview of Spectre. And it's everywhere. Because any high-powered processor these days has a branch predictor, so hello, you have to deal with that. Spectre is an attack on an idea. It actually, if you look at the original Spectre paper, there are no exploits in that paper. There are no Spectre exploits in the wild that way, yet. It's an attack at an idea. Basically, the idea of branch predictor has a nasty security consequence. And then that year, if it wasn't enough, there were 2 more that I'm not talking about. Yikes. Right? Like, that's kind of nasty. So if you make a CPU, you're affected by this. So what do? Well, there's no good news here. At least not in 2018. We need new CPU science to deal with this. Because this is such a basic attack on such a basic idea that now what? Well, now what? One of my mentors from 20 years ago had a good sentence. When in trouble, when in doubt, run in circles, scream and shout. Okay? This is exactly what we did. When that happened, we screamed and shouted, and here's some headlines about, oh hell, my CPU is broken, wah wah. Okay? It's been 6 years. Right? So after we were done screaming and shouting and went through the 5 stages of grief, okay, it comes with acceptance. And acceptance means, okay, we have to do something about it. So we now have side channel hardened CPUs. Yay, right? That deploy countermeasures. Finally. We have new architectures that were not even a twinkle in somebody's eye when the disaster happened. So these should absolutely not have these issues. We have clean slate designs, which are chips and companies that weren't even in the business when that happened. So now when they're making chips, they should have learned the lesson. And the software people also didn't stay still. Okay. They developed mitigations just to stop this sort of behavior inside of our CPUs. So are we done? We should be done. Hoping we're done. Well, I'm standing here, so I guess we're not done. So let's look at the browser, for example. Okay. So 20 years ago, browsers looked something like that, right? You could have used your Internet Explorer to search stuff on Google and buy books and only books on Amazon, and everything else you had a dedicated app for. This is MSN Messenger, we have PowerPoint, Outlook, Bank of America. If you wanted to talk to your friends, then you would use this. For those of you that are too young in the audience to know what that is, it's a rotary phone, okay? And if you and for those of you that used one a few years ago or a few decades ago by now, and you know what that is, go Google rotary phone versus 4-year-old. I'm not sure who wins that one. Yeah, it's an awesome thing to see on YouTube. But fast forward 20 years, browsers look like something like that. Everything lives in the browser right now. We search in the browser, we buy stuff we don't need on the browser, we express our thoughts in tweets on the browser, and of course documents, banking, and everything else, which means that browsers have secrets. Browsers are arguably the most trusted component of any human-facing system. Okay, so, well, if browsers have secrets, then attackers want the browsers. Okay. So, this is how browsers used to work. You have 3 tabs, mail, attacker, and bank.com. Everything lives in one process. And when the attacker compromises that process, buffer overflow, Spectre, or otherwise, the attacker gets all the secrets. Now, there is a bigger problem here, which is, so that's bad. There's a bigger problem, which is if this process crashes for some reason, because you have a rendering bug, then it takes all the tabs with it, because it all runs in one process. Well, forget about the security vulnerability. Taking all the tabs with it is a mental health crisis, because now you lose your curated version of tabs. Okay? We don't care about security anymore. I just lost my tabs. That's like a big, significantly bigger problem. Take my credit card, that's fine. Just keep my tabs. Right? So people really, really don't like this. And because of these things, we have moved to this model where, in principle, we have one process per tab. And now, if a process gets compromised, Spectre or otherwise, for that matter, there is nothing to take. What are you going to take? It's the attacker's process. Everything in there is known or controlled by the attacker. Yeah, great. Go shoot yourself. Compromise yourself. Yay. Right? So, win, right? Maybe we actually did it right. And for a while, if you look at the landscape, then browser exploits for Spectre, all these lovely buffer overflows that we just saw with Spectre, didn't happen in the browser. There were other Spectre exploits against the kernel, against the process. Great. In the browser, actually, disaster averted. So, maybe the browser people actually were in front of the curve and the problem is not as bad? Well, no. And by the way, it were my hands that introduced this code, so I'm sorry. If you're trying to find code that looks like this to do Spectre exploits, you're not gonna find it, because that's not how Spectre looks. So, this example is very easy to understand the idea about what Spectre does, but please don't try exploiting this. You will never find this gadget. And I'm sorry, but today is how you actually do exploit Spectre. So what am I going to show you today? Well, we're going to talk about a paper called Lie Leakage that works against the Apple's M series and A series chips. These are the heavyweight iPhone, Mac chips that we have around us in a famous browser called Safari, which is the default on the Apple ecosystem. And the result is something like this, right? Here's your Google passwords for Google Auth leaking, or the contents of your Gmail. Okay, so this is kind of nasty in some sense. So, before that, we need to talk about side channel countermeasures, and how do we basically take this system apart. So, the first thing is, let's talk about this tab model. Okay, so let's say that I have an attacker tab and a bank tab. Ideally, they should live in 2 separate processes. Right, 1 process per tab. Who has 2 tabs and only 2 tabs open? Yeah, right. If you're anything like me, you have many, and then you try that on an Apple machine, you get something that looks like this. Okay? And I'm not joking. Safari's security policy, 1 process per tab until out of memory and crash. Here's Safari taking 99 gigabytes of RAM, okay, on an 8 gigabyte machine. I don't know how my student got that screenshot out. This machine is about to go. Okay? Which is actually, if you think about it, the right way of doing things. What the hell are you opening so many tabs? So 1 process per tab until out of memory, end of conversation. Okay? Well, then we have to do something better because, well, we're here to break stuff, right? So we have to be smarter about it. So let's talk about a really obscure feature called federated logins. So what do I mean by that? Well, here's a login to the New York Times. And let's say I don't want to create an account. Then what they tell me is, well, if you don't want to do it, we can reuse your Google account, right? Just click here. We'll open a new window. You can put in your Google credentials. And then we can reuse your Google account to log in into the New York Times. And if you pass the Google authentication, then a login token is sent back to the New York Times, and now you can go and read stories on the New York Times. Okay. Awesome, right? So these are 2 processes, in principle, 2 websites, therefore needs to be 2 processes, and they clearly need to communicate between them somehow, because one invokes the other and gets a login auth back. Yeah. Safari has no inter-process communication. It's simply not anywhere in the code. We looked. So what black magic do we have here? Well, the only way to do this, if you don't have inter-process communication, is to put them into the same process. That's what they're doing. Okay? Yeah, great. Awesome. Because now if attacker.com opens bank.com, bank.com comes to live in the process where attacker.com lives. Great. Great isolation policy, everybody. Okay. So that's that. The next step is, okay, so now it lives in the address space. We actually need to bypass all the side channel countermeasures on how to actually get our data out. Okay. So side channels usually based on timing events. People like me became really, really good at distinguishing cache misses from cache hits using time. And cache hit is about 20 nanoseconds. Memory cache miss or a memory hit takes about 100 nanoseconds. So if you have cycle accurate timers, you should be good when it comes to distinguishing these events. And then, as you saw, you use the cache footprint as a side channel to get the values out from under the speculation. Okay. Big story. Alright, fine. Here's a clean and simple idea that actually we were hoping will hold water. Let's just kill the timer. So what do I mean by killing the timer? Well, if you're an Intel CPU, you are committed to providing cycle accurate timings. It's in the spec. If you're an Apple CPU, you don't have to make that commitment anymore. So Apple provides 42-second timer to user space programs. 42 nanosecond accurate timer, you're trying to distinguish a cache hit from a cache miss. So now this is 1 tick versus 2 ticks. Signal is there, kinda noisy, but it's workable and doable. But when you start going into the browser, then that guarantee you can back off even more. And you see Chrome providing 100 microseconds, Safari providing 1 millisecond, and Tor going even more crazy and saying 100 millisecond timers is all you get. Good luck with a 100 millisecond timer, distinguishing cache misses from cache hits that operate on nanosecond resolutions. You're not gonna see that signal. Okay, well, that's actually a nice, clean idea. Except, do we even need timers? Right, I'm a university professor. We like asking basic fundamental questions that matter absolutely nothing usually. Okay? But this is outrageous. Like, do we even need timers to do all this work? Well, no. There are many ways to measure time. One of them is using concurrency. Okay, you set up a race condition and you either win the race condition or lose the race condition based on the status of the cache. Because, well, guess what? If the computation is cached, it runs faster than an uncached computation. So just set up a race condition that falls one way or the other way based on the status if something is cached or not. And alright, great. Here goes the timer. You can do Spectre without timers. Here's Spectre running on Tor with absolutely no timers. Ideological or otherwise, just race conditions. Yeah, great. Who had that idea of killing the timer? What was the point of that? I don't know. Well, end of point. You don't need timers. Those that tell you that side channels require timers, show them that. Alright, so poor cat got shot. And now he's actually kind of happy. End of side channel countermeasures. The interesting part comes from the people that actually try to stop code reading out of bounds. And that is where actually most of the nice work comes in. So the side channel countermeasure people messed up. But the isolation people actually did a good job. So let's say that attacker.com opened back.com and now they live in the same process. Great, right? Attacker wants the password. That's what attackers do. They want the password. Except it's JavaScript. All pointers are 32-bit because JavaScript is a 32-bit language. And different websites live in different 4 GB cages. And that's not by accident. That's the whole point. Even if I put you in the same process, I'm not going to put you in the same 4 GB cage. And in fact, I'm going to leave one cage between every process, so that even if you're at the end of the cage, there is no way you can overflow towards the start of the next cage. Okay, and now you 32-bit critter, how can you even fathom a 64-bit pointer? There is no such thing. Okay, so even if you got that, good luck. Now, of course, what you want is a 64-bit pointer, then this starts happening, but there aren't any. It's a 32-bit language. Okay, that's actually where the interesting part comes in. Okay, so what happens when you access an array under the hood in JavaScript? Well, the code is compiled by Safari to look something like this, and here's my array as a class. You check the type. Well, it's an array, nothing to see here. Then you check if the index's length is less than the length. Fine, great. Then take the base pointer for the array, add the index, dereference, return the value. So what do we have here? Well, the base pointer is an internal value from Safari. Safari is a 64-bit application. So it is a 64-bit pointer, but it's not a JavaScript pointer. It's not a JavaScript value. It's not a JavaScript property. It's not even represented as JavaScript. It's part of the interpreter. The interpreter is 64-bit. Okay? But you cannot even think about that value as part of you can't even think about that value as part of JavaScript. The index is 32-bit. You can control it, but it is only 32-bit. So now, you still can't read beyond 4 GB, even if you buffer overflow this entire thing, speculatively or otherwise. That's the whole point. Yeah. Great. Shit. Stuck. Okay. Well, let's talk about attacker class. It's an object. It's not an array. I'm going to say this again. It's an object. It's not an array. Now I'm going to ask you, what's attacker class? It's an object. It's not an array. Then what's this? What? It's not an array. What? You can you do that to an object? No, so what's that? It's a syntax error. What the hell are you doing? It's a syntax error. What the hell do you think you're doing? It's not an array. Okay? So you will be yelled at. Eventually. So let's see how that code runs. Okay? And let's say that the situation in the cache is that you have an L3 miss on the type, but everything else is a hit because you're just on the boundary of a cache line. Then the situation is something like that. So now what? Well, you have a branch predictor, of course, because for the if of the type check. We can't decide on the type right now because we didn't arrive to the cache yet. Well, what happens usually to type checks? They usually pass. Okay, great, keep going. And now this fake pointer actually starts playing a real pointer on TV, and you get arbitrary reads under speculation. Okay, this is what a speculative buffer overflow looks like. This is a speculative type confusion attack. Spectre, for all of you that are thinking about it, it's not a buffer overflow. It's a speculative type confusion attack. You can shove objects into functions of the wrong type, and the function doesn't know. That's what this is. And the result is that now you have 64-bit reads, and you can even do that reliably. Because, well, this you do this, you get a 64-bit read, but eventually it will discover that, hey, what do you think you're doing here? It's a syntax error. Right? It still is a syntax error. You get yelled at, the thing will crash. Eventually. So you can do this once. I don't like doing things once. I want to do this reliably. So the reliably version of this is just wrap the whole thing in inside a false but predicted to be true statement. Take your attack code and wrap it inside an if false but predicted true. So then what happens? This whole code ran, this path ran, you got the value you wanted, then it starts going crazy and starts throwing an exception, except eventually the outer speculation resolves and goes like, nothing to see here, we're done. Okay? This is what's called speculative hiding. And if you think about it, the first time we did this, our brain breaks. It's a nested if statement, right? How nerdy can you be about a nested if statement? Okay, you're seeing an attack that uses a double nested if that has 4 execution passes, and we just exploited 3 of them. Ouch. Right? It's a nested if statement, guys. How complicated can this be? Okay? But this works. It works reliably. On the time of writing, Safari 17, iOS 17, macOS Sonoma, unmodified, all countermeasures enabled, latest at the time of writing. That's your laptops and mobile devices going, and the Apple ecosystem does not allow for any other browser but iOS but Safari on iOS devices. So if you have a mobile device, this is 100% of them are vulnerable to this, and this leaks at a rate of around 10 to 20 bits per second, rather accurately. And you can get passwords out like that. Why? You spawn a Google login, and the password manager will happily autofill the password into the text box for you to grab out of the process address space. And you can do the same with any built-in credentials, for example, credit cards. And as a special surprise to this conference, let's see how you can bypass two-factor auth with this thing. Does this play? Okay, so this is the M3. And let's go to Facebook, and the last pass happily autofilled the credentials. Okay, a few minutes later, you scan the whole address space, and eventually you will find the credentials sitting in that address space. Okay, so we found the password, which is not that interesting. in the sense of like the password is in the other space, you read the other space, you get the password. So let's try logging in. So we logged in, and we get a second factor auth that is being sent through an SMS to our phone. Thing is that you can, and here it showed up on the phone. Thing is that on Android devices, you can pair them with your laptop to read SMSs from your phone through Google. So now, if you do exactly the same trick again, but this time on the web page, on Google's web page that lets you read SMSs from your phone on the browser, then guess what lives there? The second factor token. So this is in the address space, and there is actually no need for even a credentials manager. It just lives there. So you can take that as well, just to run the attack again. Not that fast, need to earn it yet. And now you can log in, and you can disable that thing so it doesn't bother you again. Okay. Alright. This is where I'm gonna stop. We haven't learned the lessons. There is much more to come that I can't talk about because it's under embargo. Yeah, stuff leaks. Side channels are fun. It's cat and mouse game again. No. CPUs are still a problem. If you want to learn more about us, drop us a line at architecture.fail, because that's my group's website, or you can have my email address. And with that, I'm going to stop and give Ankrist back some of your time.
Thank you so much, Daniel. I'm certain we should have some questions from the audience. We do have one.
Thanks for the great talk and the interesting research. So my question is, you said the rate at which you can read is 20 bytes per second, right?
Yep.
So I guess the password is at some random address in this 4 gigabyte range of the other tab.
Yep.
How long does it take realistically if you just don't know where the password is stored to read it?
So it's not very random.
Okay.
And what you do is you basically do a binary search with ever bigger steps until you find something that you recognize, at which point the offset to the password is constant.
Okay.
And how do you find something that you recognize? Well, you can render that page yourself, right, on a separate machine, so you know the offsets within a page. So it's minutes, basically.
Okay.
Despite that leakage rate.
Thanks. Nice idea.
Thank you. We've got a question from here.
Hi, thanks a lot for this very interesting talk. I was wondering, does the eye leakage attack also works when the victim tab, so to say, lives in a private window or some other kind of container tab?
So, no, but the whole conversation, it doesn't play like that. So let's say you rendered attacker.com, and I would like to take something from the victim tab, me attacker.com. I just window.open attacker.com, and attacker.com comes to live with me. I don't need to recycle that random victim.com that is open somewhere else. I don't care about it. I will open my own copy.
Okay, so basically, the user should be tricked into visiting attacker.com and then entering their credentials in a window that's opened by attacker.com.
Half true. Yes, it's a one-click one, so the user should be tricked into going into attacker.com. After that, the password manager automatically enters the credentials, because it is really victim.com that is being rendered. So the password manager will enter the credentials without user interaction, at least for the case of LastPass.
Unless, of course, you configure the password manager to not fill anything.
To not do that, yes.
Yeah. Thank you.
Any more questions? We've got one here.
So you don't know the value of the base pointer, and you're going to enter some random values there to search for something. So how do you not hit segmentation faults if you don't know the memory space?
You do. You absolutely do. But remember, this all happens under speculation, and the outer speculation is if false but predicted as true. So when the outer speculation
that's
resolves,
how you get around that. Okay.
Yeah. That's what's called speculative hiding.
We have a last question. 2 questions.
Yeah. Thank you for the talk. So some browsers already have a so-called cross-origin opener policy, which I guess some would kind of wants to limit like side-channel attacks as well. So have you looked at this, and is there like a way to get around this? Or
so course headers do limit this. Okay, the problem with course headers is they break the internet, and if you'll be because different windows need to talk to each other. And if you look at how many web pages actually serve cores these days, you're under 1%.
Yeah. So the cross-origin opener policy, not the course. Okay.
Yeah. So this should make life better, except you need to rewrite your website to not actually use cross-origin resources, and not a lot of them do that yet.
Yeah. Okay. Thanks.
Okay. Why go for plaintext passwords in form fields when you can go after cookies? Are there any protections for cookies?
Good question. Yes, cookies is the one thing we can't actually go after. Cookies live in a separate process called the networking process. That is not the rendering process. Good luck getting code execution on that process. Yes, they were really, really careful about the cookies. Otherwise, you're right. How the hell is a password? Just go after the cookie.
Thank you, Daniel. Please give another round of applause to Daniel.